Okay, great. So let me briefly start with a review of what we did in last class. In the last class, we were looking at general waveguide-based devices, and we were looking at some properties of the scattering matrix of the waveguide-based device, as would be given by some very general properties of Maxwell's equation. So in particular, we studied three properties. So we studied matrix. So we studied the first property as a property of unitarity. That was S dagger S is equal to identity. So this was a consequence of energy conservation, right? And obviously this would hold if the device is lossless. So it has no gain or no loss. So it has no gain or loss, right? So in that case, the scattering matrix of the device would be a unitary matrix. So this was the first property that we looked at. Then we looked at reciprocity, which essentially told us that S is equal to S transpose. And this would be valid as long as your permittivity is reciprocal. And for scalar permittivities, this is always true. So in this class, we'll mostly confine ourselves to looking at scalar permittivities. So this is always true. So breaking reciprocity requires, more effort. You need to do more work. You need to use, either some external mechanisms like applying magnetic field, or you need to maybe go away from the general simple linear system picture. So you might need to apply time modulation or use some nonlinearity and so on. So this is kind of beyond the scope of this class, but as long as you have a scalar permittivity distribution, which is, like something that you can describe with a refractive index, your reciprocity would always hold, irrespective of how you choose the geometry of your device and irrespective of whether your medium is lossy or not, right? And finally, we looked at time reversal symmetry, which gave us a condition that S, the conjugate of S, which is basically take every element of the scattering of the complex scattering matrix and make it do its conjugate, is equal to its inverse, right? So this is what time reversal symmetry gave us. And this is true as long as your epsilon, your permittivity is real, right? So if your epsilon is real, then your system will behave will have time reversal symmetry. So these were a few things that we derived from. So we looked at their counterparts in Maxwell's equations, and then we looked at the counterparts, what the consequences was for scattering matrix. So let me remind you about the time reversal, what the statement of time reversal was, because we're going to use it today. So if you recall, time reversal essentially said that if E x comma t and h x comma t satisfy Maxwell's equations, right? So this is time reversal symmetry, not time reversal. So time reversal symmetry, right? Then E star of x comma minus t comma negative of h star of x comma minus t also satisfy Maxwell's equations, right? So this is the statement of time reversal symmetry, right? So this operation, so the operation E of x comma t and h of x comma t going to E star of x comma minus t and negative of h star of x comma minus t. This is called a time reversal operation, as we looked at in the last class. So you're essentially changing the sign of t. So you run your Maxwell's equations in forward, and then you take the same solution that you get as a function of time and think about running it backwards, right? That's what time reversal essentially means. So this is a time reversal operation, and what time reversal symmetry told us was that the Maxwell's equations are invariant under the time reversal operation. So if you apply this time reversal operation, the resulting fields will also satisfy Maxwell's equation. So that is what the statement of time reversal symmetry was. Okay. And if we impose this on the specific waveguide-based device that we have been talking about, which has some scattering region, and you have a bunch of input and output ports coming into the scattering region, then it told you that the complex conjugate of the scattering matrix was equal to its inverse, right? So this is what we did in the last class. So in this class, we are going to start looking at more specifically systems made out of, more specifically systems made out of cavities and waveguides, right? So instead of confining ourselves to a general waveguide based device, we are going to make our problem a bit more specialized because we are interested ultimately in understanding cavities and see how it goes. So in today's class, we'll work through a simple example of a one-port device, right? So this is section 3.21 of your course notes. And in your homeworks, you're going to be doing this for a more complicated device. It'll be a Fano resonator. So you'll do all the calculation that we do in class, repeat it for Fano resonator and see how you can develop a couple mode model. And there is a more general treatment of N-port device given in the lecture notes. So the basic ideas of how to develop couple mode theory, we'll discuss it today. And there are various extensions of it present in course notes and homework that you'll work on your own to give you a better idea of how to use it in practice. So, but the basic ideas are going to be the same as that of a one-port device. So we'll restrict ourselves to that, right? So the device that we'll think about is basically you have a single cavity, right? So you have a cavity, let's say it can be anything. It can be a photonic crystal cavity, it can be a Bragg cavity. So we are not really confining ourselves to any particular kind of device, but the general cavity formed by putting mirrors around some region in space, right? So, and we are going to assume for the time being that this is a single mode cavity. So we are focusing on just one mode of the cavity, and going to multi-mode cavities essentially, but just like looking at different many cavities instead of just using a single mode cavity, okay? And what we will imagine is that we have a waveguide that is interacting with this cavity, right? So you have a waveguide that is coupling to the cavity. And so we'll assume that this waveguide is the only channel that this cavity couples to. So this cavity has pretty much perfect mirrors everywhere around it, except for this region where you have a waveguide, right? So then it is able to interact with the waveguide and it's going to lose energy into the waveguide. So it's not a lossless cavity, it is a lossy cavity, but all of its losses are going to be in the waveguide. So now we are going to start trying to develop a simple model that can describe this coupled system, right? And this is going to be like a fundamental building block for more complicated systems. So if you have a single mode cavity, as we discussed in the first few lectures, that you can describe its dynamics by a single number, right? It's a single mode cavity, so the electric field inside the cavity is going to be proportional to the cavity mode. So the electric field inside the cavity can in general be written as some complex number times the mode, the cavity mode, right? So let's call it E cavity of X. And this complex number A is going to be a function of time, right? So this is going to be a function of time. It's going to be changing with time, right? So if in the first few classes, we wrote down a more general form of this equation, which was summing over all the different cavity modes where we were using completeness of the cavity, right? So if you remember, the cavity modes were complete. They formed a complete set of functions for any field inside the cavity. So your electric field could be expanded onto this complete set of functions for a lossless problem, right? And we are now looking at a single mode cavity. So we are imagining this toy model where I just have one mode. So that means that the electric field inside the cavity within the regime of interest can be described by just one complex number, right? A of t. And this A of t is something that varies, that in the absence of the waveguide would satisfy a harmonic oscillator equation, right? So let's say, so in the absence of a coupling between waveguide and cavity, right? So if we assume that the waveguide and cavity don't couple to each other, then the cavity is completely lossless, right? So the cavity is completely lossless, and consequently, it would just behave like a simple harmonic oscillator. So you would expect your A of t to satisfy a simple differential equation, which is minus I omega c times A of t, right? So A of t just varies as exponential minus I omega ct. So as compared to what we did in the first few lecture, where we wrote down a differential equation for the real field, so where we got a second order differential equation. So remember, in the first lecture, we got something like a simple harmonic oscillator equation, right? But this is assuming things are real, right? So where you can go into the phasor representation of this uh, of this differential equation, and then you will just end up with something that is oscillating at a frequency minus that is oscillating at omega c, but it'll be a complex exponential, right? So it's a completely equivalent representation, right? And you could imagine that in the waveguide, you have some input. Let's say in time domain, we send in a forward propagating mode, which is b plus of t, and we get out a backward propagating mode, b minus of t, right? So we send in a signal, that a waveguide mode that goes in scatters of the cavity, and it comes back, right? So if the cavity is not interacting with this waveguide, then you can imagine that there is like a perfect mirror sitting here. So your input is going to just be equal to the output, right? So you can write down an equation for your waveguide, which is essentially that the scattered field b minus of t is equal to, well, in general, there'll be a phase exponential I phi times b plus of t, right? So whatever the phase that the mirror gives me, right? So because it's a perfect mirror, you're just going to get a phase on reflection. You're not going to get anything else. But for simplicity, let's assume that this phase is, or rather, let's actually keep this phase. So we'll work with this phase, right? So this is just the phase of the mirror that the waveguide sees, right? Okay, so if you have no coupling between them, so that means you have some kind of an ideal mirror sitting here. This cavity just oscillates at frequency omega c, whereas the input of the waveguide is just reflected with some phase to give you the output, right? Does this make sense? Are there any questions here?
What is the phase of the mirror?
Well, it can be any, that depends on the design of your mirror, right? So it can be, so for now, that's why we are keeping it arbitrary. So for example, if this boundary was a PMC boundary, you'll get phase equal to 0. If this was PEC, you'll get phase equal to pi, right? So it depends on how you design the mirror that or what the phase is, right? So for Bragg mirrors, for example, you might get some phase that depends on how long the mirror is and so on, right? So we are just keeping it very general. We don't want to specialize to any particular structure, so that's why I'm just putting some phase exponential I find. Does this make sense, right? Yeah. So this happens when the two systems are decoupled, right? So this is we are ignoring any coupling. So this is your equations of motion for a decoupled system. Now let's develop a model for a coupled system. Right? So what happens when you couple the cavity and waveguide to each other? Well, the cavity is going to start feeding some input, some output into the waveguide, and the waveguide is also going to induce some loss in the cavity, right? Now, when the waveguide and cavity couple to each other, there is going to be some loss in the cavity, and the cavity and the waveguide input and output would be altered by the presence of the cavity amplitude A of t, right? So let's write down a model, right? So there is no proof of this. I'm just simply writing down a model for this coupled system. And so let's write down a model for our dynamics. So let's say the equation of motion that described the cavity, which was minus I omega c A of t, it is going to get a decay term. So let's say it gets a decay kappa. Okay, so you get a decay term minus kappa by t A of t. But at the same time, you also have to account for the fact that although this waveguide is allowing for the cavity to decay, it is also going to allow the input from the waveguide to interact with the cavity. So let me add the input with some coupling constant xi, which I've introduced, b plus t. Okay, and similarly, the output that is coming out of the waveguide will now be the output due to direct reflection from the mirror, exponential I phi b plus t, plus there is going to be some contribution of the cavity mode A of t. Okay, so I have introduced 3 parameters here in my model, right? So the first parameter is kappa. So we have 3 parameters. So let's just go through this one by one. So the first parameter is kappa that tells us what is the decay rate induced inside the cavity, right? due to the interaction with the waveguide, right? So we expect physically that the moment we switch on this interaction, the cavity amplitude should start exponentially decaying. So we add in a term that induces an exponential decay in A of t with decay rate kappa, right? So we also introduced a parameter xi, and this parameter tells me how much is the input to the waveguide affecting the cavity amplitude, right? So let's call this is coupling from waveguide input to the cavity amplitude, right? And we introduced a parameter lambda, which is this parameter here, which tells us how much is the cavity amplitude affecting the waveguide output, right? So we have one parameter which is telling us how much is the waveguide input affecting the cavity amplitude. The other parameter is telling us how much is the cavity amplitude affecting the waveguide output, right? So this is coupling from the cavity amplitude or cavity mode to the waveguide output. And while we have assumed them to be three different parameters, you would expect that there are some very important relationships between these parameters that would restrict these parameters greatly. And as we'll see in a minute, that if we just apply time reversal symmetry and energy conservation and reciprocity, the three properties of Maxwell's equations. So if we ask that this model satisfies time reversal symmetry, reciprocity, and energy conservation, if as soon as we know the decay rate of the cavity, we know the incoupling and outcoupling parameters as well. So the decay rate of the cavity completely determines how the incoupling from the waveguide to the cavity and outcoupling from the waveguide into the from the cavity into the waveguide are going to be. Okay, so let's start working through that one by one. And before we start doing that, let me make a small note on units and normalization, because this is important. Right? So as you can see here, we have written down all our dynamics in terms of these amplitudes, which is the amplitude of the waveguide and cavity mode. So A of t is the amplitude of the cavity mode. So the electric field inside the cavity mode is A of t times the mode profile of the cavity, and B minus and B plus are also, as we discussed in the last class, the amplitudes of the forward and backward propagating modes in the waveguide. So the actual electric field would require you to multiply these forward and backward propagating amplitudes with the forward and backward propagating modes, right? So of course I can choose the normalization of my electric field modes for the cavity modes and the waveguide modes to be as I like. But we are going to, in this lecture, assume a power and an energy normalization, right? So we are going to assume that the cavity mode is normalized such that, well, if I just take the magnitude of A of t squared, magnitude of this number, A of t, is the energy inside the cavity. Energy inside the cavity, let's say in joules, although that doesn't really matter, right? So we are going to choose our cavity mode amplitude in such a way that mod A of t squared tells me what the energy inside the cavity is. In other words, if A of t is equal to 1, that means that the energy inside the cavity is 1 joule, right? So that's how we are going to choose what the mode profile of the cavity is. It's just a normalization, right? And similarly, and we also, sorry, so this is 0.1. And we assume that the waveguide normalization is chosen well such that b minus of t squared or b plus minus of t is the power, well, in watts, let's say in SI units, carried by the forward and okay. So Uh, Please note that the energy of the field inside the waveguide doesn't make as much sense because the waveguide modes kind of uh, sorry, it does make sense if your B plus and B minus T have some pulse shape and so on. But it is very convenient to talk about the power inside the waveguide because you would imagine the waveguide as taking as waveguide mode as propagating in a direction and carrying some power through the waveguide mode cross section. Whereas the cavity by itself is meant to keep electric field in a fixed spatial region. So we will almost always talk about the total energy inside the cavity, right? So that's why we have these slightly different convention for choosing power in one and energy in the other. You could modify this normalization, of course, but this is the most convenient to work with. Okay, so this is how we are going to assume what our normalization is going to be. So the units of A of t is just square root of energy, so it's going to be square root of joules, and the units of B plus minus of c is just square root of watts. Right? Does this make sense? Right? This is just a consequence of the way we are choosing a normalization. And then you could immediately from these equations, so let me copy these equations here. Right, so you can then immediately from these equations tell what the units of the parameters that we have introduced are, right? So what are the units of kappa? Well, so kappa is a decay rate. So it's obviously the units are inverse of second. So it's S second inverse, right? Because it relates the derivative of A with A. So it's going to be inverse of seconds. What are the units of the incoupling and the outcoupling coefficients? So the incoupling coefficient relates derivative of A of t to B plus of t. So the units of, so units of xi, so for example, units of xi is equal to unit of dA by dt divided by unit of B plus, right? And so dA by dt is going to be square root of joules divided by second, right? Because A has units of square root of joules and units of B plus is square root of what? So if you work this out, this just becomes S square root of a rate. So xi is going to be square root of a rate, right? So this is important. And similarly, you can show lambda is also, this is unit of B minus divided by unit of A. So this is also going to be, so this is square root of watt divided by square root of joule. So it's also going to be square root of a rate. Okay, so kappa is a rate and the incoupling and outcoupling coefficients as we have defined are going to be square roots of rates. Okay, fine. So this is one note on normalization. So this is what we're going to assume in the lecture. Now, so let's start by now thinking about what are the relationship between these different parameters that we have introduced. So we have introduced 3 parameters, but they are going to be related to each other, right? So they can't be arbitrary. And so intuitively, you expect, let's say, if the decay rate is large, that means that the waveguide is coupling strongly to the cavity. That's why the decay rate is large. And therefore, the incoupling and outcoupling coefficients should also become larger and larger as the decay rates become larger, right? And you expect there to be some relationship between the incoupling and outcoupling coefficients as well. So let's start by trying to think about the consequences of energy conservation. Okay, so what does energy conservation tell us? So what energy conservation essentially tells us is that the total energy of this cavity and waveguide system should be conserved, right? So because the cavity and waveguide are interacting with each other, while the individual energy might not be conserved, so the cavity by itself might appear to be lossy and the waveguide by itself might also appear to be lossy because it is going to interact with the cavity, but the total energy of these two systems put together should be a constant, right? So let me imagine the following problem, right? So let me solve a very simple problem. That is, let us say that in this system that we have, let us start with some unit 1 joule of energy inside the cavity. Okay, right. So we start with some energy inside the cavity, and let's say that initially at t equal to 0, there are no fields inside the waveguide, right? So I just somehow, it doesn't really matter how, I give some energy to the cavity, 1 joule of energy in the cavity, and I don't excite the waveguide at all. So what will happen? Well, this energy is going to decay into the waveguide mode, right? So the energy is going to decay. In particular, to the backward propagating waveguide mode, right? There is no forward propagating waveguide mode because you have to send in a forward propagating waveguide mode. But if the cavity is decaying, it can decay into a backward propagating waveguide mode, right? So the amount of energy that I had initially in the cavity at t tending to infinity will all be energy that is propagating inside the waveguide. Okay, so let's solve this very simple problem. So because you don't have any forward propagating waveguide mode, I can use the first equation here and set b plus of t to be equal to 0, right? So since there is no forward propagating waveguide mode, our equation of motion just becomes dA by dt is minus I omega Ca minus kappa by 2a. Right? So here we are looking at, so let me write this down. We are looking at a simple decay problem. Right? So we excite the cavity at t equal to 0 with some energy and watch it decay. Okay. And this equation is very easily solved. So the solution is just going to be a of t is equal to a of 0 times exponential minus I omega c plus kappa by 2t. Okay, so you have some oscillations with the cavity frequency and a decay with time because of the losses. Okay, and then from the second equation, which is this one, you can calculate what is the backward propagating waveguide mode. So because you don't have any forward propagating waveguide mode, your b minus of t is just going to be equal to lambda times a of t. So that is lambda times a of 0 times exponential minus I omega c plus kappa by 2t. Does this make sense? Right? So for this very simple decay problem, we don't have any excitation because I'm not purposely putting any excitation in the forward propagating waveguide mode. I start with some energy inside the cavity and then it decays into the waveguide, right? So what is the power inside the waveguide at time t? Well, power inside the waveguide at time t is just because of our choice of normalization, the square of the forward backward propagating waveguide amplitude. So that is just equal to modulus of lambda squared times modulus of a naught squared exponential minus kappa t, right? And what therefore is the total energy that is emitted into the waveguide. So the total energy inside the waveguide, is going to be an integral of this power from 0, that is the time at which the cavity started to decay, all the way up till infinity, right? So that's going to be 0 to infinity, p of t dt. And if you just plug in what we have on top here, it's very simple. It just gives you mod lambda square times mod a naught square divided by kappa. Does this make sense?
Yeah.
Right, so this is very simple algebra. So this is the total amount of energy that is being carried away by the waveguide. But if energy conservation is true, this should be equal to the total amount of energy that we started off in the cavity with, right? So we started off in the cavity with some amplitude a of 0. So what was the energy in the cavity at t equal to 0? It was just equal to mod a of 0 squared, right? And these two have to be equal because the total energy in your cavity plus total energy in your waveguide at any instant of time should be equal to, should be the same, should be constant, right? It should be conserved. So at t equal to 0, there was no energy in the waveguide. All the energy was inside the cavity. So this is energy at t equal to 0. And this is the total energy after energy at t tending to infinity, right? After the cavity amplitude has completely decayed into the waveguide mode, right? And so for these two to be equal, this immediately tells you that the coupling between the cavity and the waveguide is related to kappa, right? So the square, the modulus square of the coupling constant of the cavity to the waveguide, the outcoupling constant, right? So this parameter lambda here, which tells you how does the cavity mode affect the waveguide mode, is constrained to be equal to kappa, right? So this is one immediate conclusion that we get as a consequence of energy conservation. Does this make sense? Right? And this is completely intuitive. You can see there's a square because of a choice of units. So if you make kappa equal to 0, so that is if you don't have any decay, that means that the cavity automatically is decoupled from the waveguide, and therefore you don't have any outcoupling. We completely expect something like this. Okay, so this is the consequence of energy conservation. Okay, so well, so that this means that, so therefore we can write lambda. In other words, it's square root of kappa, right? That's the magnitude with some phase exponential I theta, which I cannot determine this by energy conservation alone. So we cannot determine this by energy conservation. Conservation alone. So this phase still needs to be determined, but the magnitude is definitely equal to square root of the decay. Okay. Okay. So this makes sense, right? Any questions here? So this is a very simple consequence just of energy conservation. We didn't do anything at all. Okay, so let's move forward. Well, Maxwell's equations should also satisfy time reversal symmetry, right? So we looked at energy conservation, but let's now think what time reversal symmetry tells us about this model. Okay, so let's look at consequences of time reversal symmetry. Okay, and so this is going to be slightly trickier than applying energy conservation, but very, very similar. So let's again look at the same problem that we looked at here. So we looked at a problem where you have some amplitude A of 0 inside the cavity at t equal to 0, right? You're not exciting it through the waveguide mode. So there is no forward propagating wave. And you watch this decay into the waveguide mode to give you a backward propagating wave, right? So this is a problem we just solved. So let me write down the solution. So we wrote A of t as A of 0 exponential minus I omega ct exponential minus kappa t by 2. And we wrote B minus of t as equal to, well, we had lambda times A of t, but lambda we discovered has a magnitude of square root of k because of energy conservation. So let me put that in. So square root of k exponential I theta. This is nothing but lambda times this coefficient. Okay, so this is the forward propagating solution, right? So this is a solution that we obtained by just solving our couple mode equations, right? So and of course it goes without saying that this problem starts at t equal to 0. So we are going to assume that there is nothing before, right? So this is only valid for t more than equal to 0, and before t equal to 0, our cavity initially had no energy, right? So that's fine. That's just like a choice of our time reference. Okay, so now let's look at time reversal. Okay, so let's look at time reversal. So if you remember, what was a time reversal operation? So in time reversal, what we would do is we would replace E by E of x comma E star of x comma minus t, right? So E would be replaced by E star of x comma minus t. Okay. So imagine that what the forward problem was that we have cavity, which is decaying into the waveguide. Therefore, the time reversal problem is we take the amplitude that has decayed into the waveguide and send it as an excitation to the cavity, right? So for the time reversal, what we will need to do is that this t going to minus t and the conjugation is the same thing as changing the forward propagating mode and making them into backward propagating mode. Does this make sense? The conjugation on the electric field would take an exponential I beta z, which would take forward propagating mode and send it into a backward propagating mode, and a backward propagating mode into a forward propagating mode, right? So what was our B minus of t would now become a B plus of t, right? So our B plus of t, which is a forward propagating mode, would be equal to B minus of t with the conjugate. Does this make sense, or are there any questions here? So think about this a bit. So when we do a time reversal, we have two operations that are being applied, right? So we have sort of electric field E, remember, is equal to a sum of B plus times a forward propagating mode times a B minus into a backward propagating mode inside the waveguide, right? So when I do a conjugation on this, right, I get a conjugation operation on all of them. This forward propagating mode becomes a backward propagating mode, right? So, so let me actually write this as B plus tilde, so to indicate time reversal, right? So this is E going to E tilde, so you can think of it as rather saying E tilde of x comma t is equal to E star of x comma minus t, right? So because the forward propagating mode becomes a backward propagating mode and a backward propagating mode becomes a forward propagating mode, for the time reverse problem, the B plus that we are going to use is going to be the conjugate of B minus with the time t flipped as well. Does this make sense? So the time t flipping is coming from t going to minus t here. And the fact that my forward propagating mode is becoming a backward propagating mode and vice versa is coming from the conjugation operation. Okay. So what is B minus? So which tells us, so thus B tilde plus of t is simply equal to, now let's write this down properly. So our B minus of t was equal to this expression for t more than equal to 0. So when I do B minus of t, then I will get t for t less than 0. I get the conjugate of this expression. So I get square root of kappa exponential minus I theta a star of 0 exponential I omega minus I omega ct exponential kappa t by 2. Okay. And for t more than equal to 0, well, it doesn't really matter because our fields were 0 for t less than 0 in the original problem, right? In the original problem, we started with some energy at t equal to 0, and then we had no fields before that, so we'll just set it to 0. But for t less than 0, it becomes a time reversal of this result here. Does this make sense? Are there any questions here? This is slightly confusing to wrap your head around, so I can pause a little bit here before.
What is the role of the E star equation?
So I'm trying to explain why B plus of minus t is chosen to be this, right? So the time reversal operation is here, right? So we take the electric field, we conjugate it and flip the sign of t, right? The conjugation inside the waveguide is the same as flipping the forward and backward propagating mode. That's what I'm trying to explain here. So if you take the electric field inside the waveguide as sum of forward propagating mode and backward propagating mode, and you conjugate them, then this E plus on conjugation becomes E minus, right? And E minus on conjugation becomes E plus, right? So in the time reverse picture, I have to take the amplitude of the forward propagating mode and treat it as the amplitude of the backward propagating mode. So I'm just trying to explain that through this equation. There's no new information here, right? And then that's due to the conjugation, but then you're also sending t to minus t, and that's where this minus t comes from. Okay.
So I can understand that you do the conjugation on the E star, but where's the minus t coming from?
Well, that's because you have, so I mean, if you imagine like B of t to its very, very narrow band, so then this is a function of t here, right?
Yeah.
And so you have, this is E star of x comma t, but the operation is E star of x comma minus t. So you have to replace t with minus t. So this becomes minus t.
Yeah.
Right? So now, right? So you have E of x comma t is equal to sum of B plus of t, E plus of x plus b minus of t, e minus of x, right? And so e star of x comma minus t is therefore sum over b plus star of minus t times e minus of x plus b minus star of minus t, e plus of x. Does this make sense?
Yep.
So if I was to write this as sum over b tilde plus of t, e plus of x, right? Then you can easily identify that the new forward propagating amplitude is this.
Right. Yeah.
Right. So that's where this is the minus t. Does this make sense?
Yeah.
Right. So then I just substituted the b minus t that I had solved from my forward problem, and I get the time reverse problem. Okay. So now you can say, well, what is the time reversed a of t? So for that, I can solve my couple mode equation. So from couple mode equations, so you have dA by dt is equal to minus I omega Ca minus kappa by 2a minus xi times b plus, right? Now we're looking at the time reverse problem. So let's solve this problem. So now we take the time reversed waveguide amplitude and we look at what is the time reversed cavity amplitude that we should be getting. So there are two ways of getting the time reversed cavity amplitude. So method one is to solve our couple mode equations, right? So because our system satisfies time reversal symmetry. So in order to calculate the cavity amplitude, I could just plug in this forward propagating b plus of t that I've calculated from a time reversal operation into my couple mode equation and get the time reversed a tilde of t. And so you can plug this in and you can solve this equation, right? It's a very simple, again, first order differential equation you can solve. And I'll write down the solution. So what you get for e tilde of t from here is going to be equal to, this is going to be xi divided by square root of kappa exponential minus I theta kappa t by 2, right? So it looks slightly complicated, but it's actually very simple. It just follows by integrating this first order differential equation. Okay, so you plug this in here and you integrate, and this is what you would get. Okay, does this make sense? And well, but this should be equal to, but because our system satisfies time reversal symmetry, the a tilde of t that we get from here should actually be equal to a star of minus t, correct? So remember, our system satisfies time reversal symmetry. So if I solve the time reverse problem, which is sending the backward propagating mode as a forward propagating mode and calculating the cavity amplitude, that should be equal to just time reversing my cavity amplitude, right? So we should be able to time reverse the cavity amplitude, which is a of t here, and get the solution of the time reverse problem. So what is the time reversal of the cavity amplitude? Well, it is simply just using this expression. This should be equal to a star of 0 exponential minus I omega ct exponential kappa t by 2. Does this make sense? So a of t is equal to this decaying exponential here. So its time reversal is going to be a growing exponential, which is what I've written here, right? Which is just this expression simplified. And this is what we get by solving the couple mode equation with the time reversed waveguide amplitude. Okay. Any questions here? So if my system is time reversal symmetric, these two have to be equal. So for time reversal symmetry to be satisfied, to hold, we immediately get that xi times exponential minus I theta upon square root of kappa is equal to 0. Right? So which means that, is equal to 1. which means that xi is equal to square root of kappa times exponential I theta. Okay, so what time reversal symmetry allowed us to do was to relate the decay rate kappa, right? So it related the decay rate kappa in our original couple mode equations to the incoupling coefficient, right? Energy conservation allowed us to relate it to lambda, and time reversal symmetry allowed us to relate it to the incoupling coefficient. Does this make sense? Any questions? So let me pause here for a bit.
Is it a physical interpretation that's kappa related to eta when we are just using the time, the reciprocity relation?
Time reversal symmetry.
Yeah, sorry.
Yeah, so the physical intuition is clear. It's like, so xi tells me, so for your time reversal symmetry to be satisfied, you would intuitively expect the incoupling and outcoupling to be equal, right?
Yeah.
And that's what is happening, right? So this, if you remember, is exactly equal to lambda. We calculated this above, this guy. Right? So what time reversal symmetry is telling me is that if I couple from my waveguide into the cavity, then it's the same thing as coupling from the cavity into the waveguide for this one port system.
Yeah.
And that makes physical sense, right? So this is just showing that in detail, right? So time reversal symmetry. And outcoupling are equal, right? And by energy conservation, we know that these incoupling and outcoupling should be related to kappa, but their magnitude is equal to square root of kappa. So if you take your kappa to 0, you consider a system which is lossless, you don't have any incoupling and outcoupling as well. Okay, so it all makes physical sense. So let's take a few minutes break here, and then we'll go to one last conclusion that relates this parameter theta. So up till now, mostly we have been able to talk about the magnitude of this incoupling and outcoupling coefficients, but we still have to say something about this phase, right? So we'll use time reversal symmetry a little bit more to be able to talk about that. Okay. If you guys have any questions, we can talk about that.
Is there any restriction on the waveguide we are trying to use? Because there are different modes that maybe cavity cannot couple to the waveguide.
No, so this is for, like, of course, right now we are assuming a single mode, but you can always add more terms into your couple mode equation and go to multi-mode waveguide. I'll show you roughly how you can do that. So in the course notes, for example, they deal with a system for a general N-port system where you have N waveguide modes coupling to the cavity, and you get a very similar system of equations. So you can think of every mode of the waveguide as being an independent port and still write down a very similar model.
Oh, so we just like decompose into a single omega, one at a time. So we're just looking at one mode at a time, like one.
Right. So one mode. So waveguide mode, you mean one, like TE0 mode, TE1 mode, or whatever, right? Yeah. So yeah, you're looking at one mode, but if you have multiple mode, you'll just have different Bs for each mode.
And different mode didn't have any coupling, right? Like
yeah. So that is how you would define a mode. Like mode by themselves are independent of each other, right? Okay. And then each mode couples to the wave cavity mode. So the cavity can mediate a coupling. So because of the cavity, the modes can effectively couple to each other, but that will fall off from your couple mode equation.
Yeah. I see. Yeah. Thanks.
Yeah. So in your homeworks, you will be repeating a very similar calculation with somewhat more complicated setup. So if you have any questions, we can talk about it. You can also discuss this in office hours, of course.
Where's the Fano resonance coming from?
Say that again.
Where's the Fano resonance coming from?
Right. So the Fano resonance, essentially, as you were just mentioning, the Fano resonance actually comes from the fact that if even without the cavity, there is like a non-trivial coupling in between your different waveguides. So essentially what happens in a phanoresonator is that even if you remove the cavity, like, so you need multiple waveguides to see a phanoresonance. You can't, or multiple waveguide modes to see a phanoresonance. You can't see it in a one-port system. You need at least a two-port system. So even if you remove the cavity, then you have a coupling between different ports, right? And then when you put in the cavity, then you see an interference of this coupling in the absence of the cavity with what happens when you put in the cavity to give you a phanorine shape. So that is roughly speaking what happens in a phanoresonator. And your homework should develop a model for that. So you can impose all of these constraints and you'll get a couple mode model which gives you phanoresonances based on the model parameters. But that's roughly speaking the idea.
Yeah.
Right, so that's an interesting problem. So that's why I will not solve it here, but in office hours, we can talk about that in more detail.
Yeah, sure.
Any other questions? Okay, so let's look at the final conclusion of this of our time reversal symmetry and finish setting up our system of equations. So for now, what we did in time reversal symmetry was we looked at the cavity field, right? So we said that let's first solve the forward problem. So we have a cavity mode, which is decaying into the waveguide. And then we time reversed the waveguide mode. So we took the backward propagating mode, sent it as a forward propagating mode, and calculated the cavity mode again. And we said that, well, this cavity, the cavity mode that I got from solving the time reverse problem should be equal to the time reversal of the forward problem, right? So that's what we did, right? So we constructed this time reversed input. Then we solved our couple mode equation to get the cavity mode on excitation by the time reverse input. And then we said that this is equal to the time reversed cavity mode. And that gave us a constraint that the outcoupling coefficient has to be equal to the incoupling coefficient, right? But for the time reversal symmetry to be perfect, we still need to impose one more condition. Can someone tell me what that condition is? So we have looked at the electric field inside the cavity. We have still not looked at one more mode in the problem. Can someone guess what that is?
The free propagating modes.
In what sense?
In the vacuum.
In the waveguide?
In the vacuum. So
but there's only a waveguide in a cavity, so there isn't a vacuum per se here.
So I guess the modes in the waveguide then?
Exactly right. So the modes in the waveguide. So remember what we did here was we time reversed the forward propagating mode to get the backward propagating mode from the original problem. So B minus of t from the original problem to get the forward propagating mode in the time reverse problem, right? But we also have a backward propagating mode in the time reverse problem, right? So we can also calculate a B tilde of minus t. So this is in the time reverse problem, right? So how do I calculate this? Well, I say this is equal to B tilde plus of t times exponential I phi plus, I'm using a couple mode equations here, right? So we have B minus of t is equal to B plus of t plus lambda times A of t, right? Plus lambda times A of t, A tilde of t, right? So the output inside the waveguide is equal to input multiplied by a phase plus the transmission plus the emission from the cavity, right? What should this be equal to? If time reversal symmetry holds, this should be equal to B star, or rather B plus of minus T star, right? So this is the backward propagating mode in the time reverse problem. This should be equal to the forward propagating mode of the original problem, right? What was the forward propagating mode of the original problem?
0.
0, right? So we were looking at a problem where a cavity mode amplitude was decaying into the waveguide. We did not have any forward propagating mode. So which means that if in the time reverse problem, I send in a forward propagating mode that is exciting the waveguide, there should be no emission into the waveguide mode, right? Because in the original problem, the forward propagating mode was 0, right? So this was equal to 0, right? Because we did not have any excitation in the original problem. So this sum should be equal to 0, right? Does this make sense? So for time reversal symmetry to be satisfied, both the fields inside the cavity and the waveguide should satisfy time reversal symmetry. And if you substitute b tilde of plus t, which we have here, we wrote this here down, we wrote down this, and you substitute a tilde of t into this equation, right? So you can do that very quickly. So you get exponential I phi times b tilde of plus t, which is this guy right here. So you have square root of kappa exponential minus I theta. Kappa t by 2 plus a tilde of t. I mean, you can use either of these expressions because they're equal. So let us use this guy here. So plus lambda times a tilde star of 0 kappa t by 2 equal to 0. We get another constraint on our coefficients, right? See, this just vanishes. And I get lambda is equal to minus square root of kappa times exponential I phi, right? And from here, we know that lambda is equal to square root of kappa exponential I theta. So this is equal to square root of kappa exponential I theta. So this gives us a relationship between theta and phi. So theta you can choose to be equal to, sorry, I made a mistake somewhere. No, sorry, this is the square root of kappa times exponential minus I theta here. This into this is sitting here. Sorry, a simple algebra mistake. So this tells us that theta 2 is equal to pi by 2 plus phi by 2. Okay. Let's just review. This gives you exponential 2I theta is minus exponential I phi, and therefore this, right? So the second constraint that says that in the time reverse problem, the emission from the cavity and the direct reflection from the waveguide should destructively add up in phase so that your output is 0, gives you a constraint on the phase of the coupling constant and the phase of the direct transmission pathway. Does this make sense? So what was phi? So if you remember, phi is just the phase that you would see in the absence of the cavity, right? So if this was perfect, you would see this phase. And theta was the phase associated with the incoupling and outcoupling coefficients. Does this make sense? So theta was the phase associated with the incoupling and outcoupling coefficients. Phi is the phase associated with the direct reflection. And for these to add up, for your time reverse problem to be actually equal to the forward problem, the input that we are sending in from here plus the emission from the cavity should add up destructively to give you 0 in the output waveguide for the decay problem that we have been looking at. And that basically tells you that 2 theta should be equal to phi plus phi. Does this make sense? Right? And this is completely intuitive because what is 2 theta? Well, if you send in an input through the waveguide, you're going to pick up one phase in incoupling and you're going to pick up another phase theta while outcoupling. And then this has to be out of phase with phi. So that's why you get 2 theta is equal to phi plus phi, right? So that's a very perfectly intuitive interpretation of this condition. But we did this, of course, more rigorously by exactly looking at what the time reverse field looks like. And this condition tells us that the phase of this incoupling and outcoupling coefficients cannot be arbitrary. They are actually constrained by the phase of this direct reflection in the waveguide port. Does this make sense? Are there any questions here?
I have a quick question.
Yeah.
I'm a little bit confused about why you pick up a phase when you couple in. Is this just some general phase we're saying you could pick up, or?
But in general, you would, yeah, this is a very general phase that you could pick up. It might as well be the theta and phi are 0 for the specific design that you're looking at.
Okay.
So, but what we are saying is that if, let's say, you have a phase on this direct reflection, right, in the limit of your cavity being lossless, then the incoupling and outcoupling coefficients necessarily have to pick up another phase.
Okay, I see.
To satisfy time reversal symmetry. You might design your system in such a way that you don't have any phase, right, on reflection, and that would mean that that will constrain that your incoupling is going to be pi by 2, outcoupling is going to be pi by 2, for instance, right?
Okay.
So, but in general, in a general electromagnetic structure, you would expect to pick up some phase and going across your mirror, right? For example. So if you imagine that there is a Bragg mirror, then you're going to pick up some phase from your input to the field inside the cavity on propagating through the Bragg mirror.
Okay.
Right. So it's a general phase, but what this is saying is that that general phase is constrained by the phase in the absence of the cavity, and that is a consequence of time reversal symmetry. Okay, does this answer your question?
Yes, thank you.
Yeah, okay, excellent. Any other questions, guys? So you see that, we started off with a very, very general model with these 3 or 4 parameters, but at the end of the day, we just have a decay rate and a phase on reflection. So, and we didn't even try and satisfy entire Maxwell's equations, but just satisfying the property of energy conservation and time reversal symmetry gave us these results. Okay, so let me collect all of these and write the final couple mode equation. So you can write the final couple mode equation for the system. Right, so you have dA by dt is equal to minus I omega c plus kappa by 2a, right? So the resonant frequency plus the decay rate. And then you have an incoupling, which, which would then be given by using this relation as well, I times square root of kappa exponential I phi by 2 times b plus of t. And you have b minus of t is equal to exponential I phi times b plus of t plus I times square root of kappa exponential I phi by 2, a of t. Okay. Does this make sense? So for a one-port model, the only 2 parameters that you need to set up this couple mode theory is the decay rate and the phase in the absence of the cavity, right? Or you can think of it as the off-resonant phase. Does this make sense?
Hi, I actually have a question.
Yeah.
Why is the amplitude of the reflection term 1? So I mean, I would imagine if your input light, some of it is being coupled to the cavity, then the reflection should be less than 1.
Yeah, so that's a good question, but the one way of thinking about this is, let's say you excite the cavity to be off resonant, right? So you excite it with a field that is very, very far away from the resonance of the cavity. Then you would expect that the amplitude of the reflection is going to be equal to 1, right? Because it's just a single port device. So what goes in goes out, right?
Yes.
So in this simple model, that is implies that the reflection here is going to be 1. You use a more complicated model where you instead of assuming these coefficients to be frequency independent, right? So constants, you could assume them to be more complicated functions of time, and then you can incorporate more effects like, the reflection is slightly different because you're coupling into the cavity. But if you assume in the limit of, very low coupling, if you assume a simple first order differential equation model, then you'll necessarily have to set this reflection.
I see. So this is because this is a weak coupling.
This is a weak. So if you're in the regime where your losses are very small and you expect these, exponential decays in your cavity, which typically happens when your losses are small, then for a one-port setting, it is completely captured by a unity coefficient here.
Okay.
Right.
Thank you.
Yeah. So, but this, of course, right. We'll look at these equations in frequency domain, and it'll become slightly clearer in a minute. Yeah. But if you have a very lossy cavity, then this, of course, doesn't hold. Then you need more complicated models to handle that. Any other questions? No other questions, right? Right. So yeah, so just to maybe make that, so to what is sitting here is the scattering matrix of your ports without the cavity, right? Because if you imagine you excited at a frequency very different from the cavity, then your cavity amplitude really goes to 0, right? If you're very, very off resonance. And then what you just get here is the scattering matrix of the ports without the cavity. So for a one-port system, that scattering matrix is just going to be unity, right? Otherwise, you don't really have a one-port system. For multiple port systems, for multi-port systems, like what you look in your homework, you can have a non-trivial scattering matrix sitting here. So if you have an actual two-port system, you could put a scattering matrix here that is going to couple different modes, and then you can incorporate the effect that you don't have unity reflection in your coupling region as well, right? But for a one-port system, that doesn't really matter. Right, so for a one-port system, the cavity is going to have unity scattering matrix. Okay, so I think so this roughly gives you how we set up the couple mode theory. So let's draw some very simple conclusions from this couple mode theory. So let's look at, for example, one thing that we can calculate is, let's say in frequency domain, what is the cavity amplitude A of omega divided by the amplitude of your input B plus of omega. So you excite your cavity with some frequency omega. How much is the amplitude inside the cavity? Well, you can get that by simply Fourier transforming these equations. You could say that if I write down Fourier transform, I get minus I omega A of omega is minus I omega C plus kappa by 2 A of omega B plus of omega. And this immediately tells you that A of omega is equal to, well, A of omega divided by B plus of omega is equal to I times square root of kappa exponential I phi by 2 divided by I times omega C minus omega plus kappa by 2. So you see that this model is, what it is telling you is that the amount of energy inside the cavity is a Lorentzian in frequency, right? So if you plot this out, you'll get a resonance at omega equal to omega C, which makes perfect sense. So if you're exciting it with an input that is very close to the resonant frequency of the cavity, you'll see that the energy inside the cavity becomes very, very large. And as you go away from the input, the energy inside the cavity becomes 0, right? Something that we completely expect. You can also calculate the one-port scattering matrix, right? So which is B minus of omega divided by B plus of omega, right? And that follows from this equation, and then you can add in the second couple mode equation in frequency domain, which is sitting right here, to say B minus of omega is exponential I phi, B plus of omega, I square root kappa exponential I phi by 2, A of omega. And then these two together give you your scattering matrix, which is simply equal to exponential I phi divided by I omega C minus omega plus kappa by 2, I omega C minus omega minus kappa by 2, right? And so this is what your frequency domain scattering matrix looks like. Now, surprisingly, you'll see that this scattering matrix has magnitude equal to 1, right? Or maybe not surprisingly. Why is this not surprising? Because it's a one-port system. If it's a one-port system, my scattering matrix, if it's a one-port system that conserves energy, the scattering matrix has to have magnitude equal to 1, right? There's no way you can have a magnitude different from 1, right? So the scattering matrix always has magnitude equal to 1. And you can also see that the scattering matrix reduces to just exponential I phi as your omega goes away from omega C. Right? So as your omega and omega C, omegas become slightly, very, very different from your resonance frequency, the scattering matrix just becomes equal to exponential I phi, which was the scattering matrix of the system without the cavity, which is what we expect. As you go very far away from the resonant frequency, your cavity amplitude is essentially equal to 0, and you're just seeing the scattering from the mirror, right? Does this make sense? Right, which is why you get an exponential I phi. And this is also why it has to be equal to 1, because this scattering matrix in the limit of omega minus omega C going to infinity also has to satisfy energy conservation, so its amplitude has to be equal to 1. Okay, does this all make sense?
Yeah.
Right. Okay, great. So of course, you're going to be playing around with couple mode theory a bit more in your homework. But there's one good thing that we can do with this couple mode theory is that, we don't necessarily need to go through all of this mathematics every time we have to set up a couple mode theory. And you can set up couple mode theory very much like, a circuit model, right? So so the only thing to keep in mind is that for every port, you have a particular relationship between the incoupling and outcoupling coefficients. That's the only thing that you really need to keep in mind. And this exponential I phi, well, typically we can assume that we choose our references such that this phase equal to 0. So I can often drop these phase terms as well. So let me, for example, write down a simple scattering couple mode theory for two-port system. And this is actually properly derived in the chapter, in the course notes. So you can read through the derivation of this, like applying all of this energy conservation and time reversal symmetry, but you can write this down intuitively as well. So imagine, you have a cavity and this is coupling to two ports, right? So this is coupling to two ports. Now you have two inputs, B1 plus, and you have an output coming out, B1 minus. You have an output B2 minus and an input B2 plus, and you have a cavity amplitude A. Well, how do I set up a couple more theory? So let's start writing it down. So we should be able to write it down without thinking much. So I have dA by dt. I need to add in terms for the decay rate of the cavity, right? And now I need to add in terms which tell me how this B plus affect the cavity, right? So there are two B pluses. So let us assume that these phases are equal to 0, when we don't have any cavity. We can assume we choose our reference plane for measuring the waveguide mode in such a way. So choose the phase of the waveguide mode so that the phases are 0. So then you just have terms which look like this, I square root of kappa, adding up. So let me say I have I square root of kappa 1, B1 plus for the first cavity, and then you have I square root of kappa 2, B2 plus for the second waveguide mode. Does this make sense? And what do you expect the relationship between kappa, kappa 1, and kappa 2 to be?
Why is the square root of kappa 1?
I'm just right. So because different waveguide modes can couple differently, right? So these two need not couple equally. So kappa here is a total decay rate, right? And you can imagine kappa 1 and kappa 2 to be decay rates into the individual waveguide modes.
Oh, it's a lambda 1.
Right. So this entire thing is lambda 1. This entire thing is lambda 2. So I'm just writing lambda 1 is square root of kappa 1, lambda 2 is square root of kappa 2, right? So from energy conservation, you expect kappa to be equal to kappa 1 plus kappa 2, right? And in fact, you can show that by a very similar exercise, right? Now, what exactly is kappa 1 and kappa 2? Well, that would depend how much these waveguides are coupled to the cavity, right? Maybe one waveguide is coupled much more strongly than the other, so the kappa of that waveguide is going to be much larger than the kappa of the other. But this is what you expect in general. If you have two waveguides, you'll have different decay rates corresponding to the two waveguide modes coupling to the cavity, right? And then you can write down equations for the outgoing waves of the individual waveguides in terms of the incoming waves of the cavity. So you'll have B1 plus. And from time reversal symmetry, now I know that the outcoupling coefficient in the first waveguide mode has to be equal to the incoupling coefficient through the first waveguide mode. So this should also be equal to square root of kappa 1 times 8. And B2 minus should be equal to B2 plus square root of kappa 2 times 8. Does this make sense? So, I mean, I did not prove that this is true. This is again in section. So for proof, you can refer to section 3.2.2 of the course reader, right? And then you see for a general n-port system, we can apply same arguments, time reversal symmetry, energy conservation, and so on to derive this format as well. But very intuitively, every time you add in a waveguide port, you are adding an additional decay term in your cavity, right? So you add an additional decay term here, and you're adding, you're just constructing an input-output relationship for every port, right? And this being equal to the third term here is just constrained by energy, by time reversal symmetry. Does this make sense? Right, roughly. So you can, sorry, go on. Question.
Sorry, I just have a quick question. In those last relations you wrote down, you, I guess, took e to the I phi to be 1.
Right, we assume phi to be 0, yeah.
Okay, is that just a safe assumption to make? Is like, in any
Yeah, you
situation?
can think of it as you can put that in, of course. You can think of it as redefining the waveguide mode electric field to absorb that phi in it. So you can define the forward and backward propagating waveguide modes
Right.
to account for the phase that they get in reflection, for instance. Right.
Okay, great.
So then you don't have to worry about that phase in the amplitude. You could put it back in if you want, right? So you could put in exponential I phi 1 here, exponential I phi 2 here. You'll get exponential I phi 1 by 2, exponential I phi 2 by 2. So whatever suits you, both work, right? Okay, does this make sense? Hello? Yeah,
Yeah.
okay,
Yeah.
great. Right, so this is, so let's say, let's say we want a slightly more complicated system. So this is a hint for homework, right? So where we have coupled cavities, right? So in your homework problem, you're asked to set up couple mode theory for a coupled cavity. You're not asked to prove it, but just write it down. So, this is some exercise. If you're trying to use these couple mode models in your own research, you want to be familiar with is just how you would write down a couple mode theory. So in your homework, for example, you look at a problem where you have two cavities coupling to each other with some coupling constant G, right? And then you have a waveguide coupling to the first cavity and another waveguide coupling to the second cavity. This is kind of the problem that you're looking at in your homework, right? So actual structure is a Bragg mirror, cavity, Bragg mirror, cavity, another Bragg mirror, right? So you have one input port here, one input port here, and then you have a coupling between the cavities. So it's the same as the format written above. So if you call these waveguide amplitudes A1 and A2, let us try and write down a couple more theory for A1 and A2 for the system. And then you have B1 plus, B1 minus, B2 plus, B2 minus, right? So how do I write it down? Well, I have, so let me start by writing down the cavity amplitude equation. So I'll have dA1 by D2 is equal to, let's say, the frequency of the first cavity minus I times frequency of the first cavity plus dk of the first cavity A1, right? So this is going to be related to kappa 1, and this is going to be related to kappa 2, right? But there is also a coupling from the second cavity, so I need to add that in. So I need to add, yeah, and this is just a choice. So I need to add a coupling from the second cavity, minus I times G times A2, right? And then I need to add my input from the first waveguide. So I have square root of kappa 1 B1 plus. Does this make sense? So the amplitude of the first cavity is affected by its coupling to the second cavity, as well as the input from the first waveguide, right? And similarly, you can write down dA2 by D3 is minus I omega 2 plus kappa 2 by 2 A2 minus IgA1. Well, why are these equal? That's in your homework, so I would not tell you why these are equal. But if you solve part A of your homework problem, of the couple mode problem, you'll understand why these are equal. And then you have coupling from the second cavity. So you have I times square root kappa 2 B2 plus, right? And then you can write down equations for B1 minus, very similar. So we have B1 plus I times square root kappa 1 A1. And B2 minus is equal to B2 plus I times square root kappa 2 A2, right? So without too much,
Sorry, just
right.
real quick. Is why I don't think I caught it. Why is it minus IG and not plus IG? Or like, what's the reason for that sign?
You could use G in general as a complex number, right?
Okay.
And then, so let's say we call this G12 instead of, let's forget about plus minus G. So let's call this G12, which is coupling between the first to second, or the impact of the second cavity on the first cavity. And you can call this G21, which is impact of the of the first cavity on the second cavity, right? These two are going to be constrained again by energy conservation, right? So if you remove the waveguides for the time being, if you remove the waveguides, you're just going to get something like dA1 by dt is equal to minus I omega 1 A1 plus G1 2 A2. And dA2 by dt is equal to minus I omega 2 A2 plus G2 1 A1, right? And for this system of equations to be energy conserving, you'll realize that there is a constraint on G1 2 and G2 1. So in fact, G1 2 should be equal to minus G2 1 star. This is something you have to work out in your homework, right? Because if you remove the waveguide, then the two couple cavities should form an energy conserving system, right? And this will just drop out of energy conservation. And then I just made a choice of writing G12 as minus I times G. This is a choice because the phases of these coupling coefficients don't matter too much. And therefore, the G21 also becomes minus I times G. So that was just a choice. But this is the more general result that you can look at, okay? Okay, so maybe that's not a perfectly satisfactory answer, but this is homework problem. So when you work through it, and we can discuss in office hours if you have questions.
I think it makes sense. Yeah.
Yeah. So energy conservation constrains these two, very similar to how energy conservation has constrained a bunch of parameters there, right? But that's essentially where that came from. Okay, so you see, like even for a complicated system where I have two cavities, two waveguides, I could write down couple more theory without thinking much about it. And then you can kind of use this couple more theory to understand the spectrum that you obtain in your homework. So in your first homework. So that's one of the goals of your second homework, where you want to use couple more theory to understand simulation results from your first homework. And that's generally the idea behind couple more theory as we discussed. So we have these very, very simple differential equation models that we can use to understand how these devices where I have a bunch of cavities and waveguides interacting with each other can behave. And you can use them in most cases to develop very physical intuition about how your system is behaving, right? Because all the parameters here are resonant frequencies, decay rates, coupling constants. You understand exactly what that means. And in most cases, these reproduce spectrums from simulations very, very precisely, right? So these are like a first tool of attack if you want to understand how a coupled system is going to behave, what its properties are going to be. You should go ahead and try and think about it by writing down couple more theory and see what your results are going to be. And then, once you have that, then you can do more precise simulations to see if you're in the right regime or you're working with the right parameters and so on. Okay, so I think this is where we are going to stop with couple more theory, right? So it's a shorter quarter. Otherwise, I would have spent a little bit more time on couple more theory to, show you more examples. But I think the homework problem will give you an idea of how you can use these ideas in practice. And yeah, please feel free to ask me any questions in the office hours, and do go through chapter 3. It has more details on setting up couple wave theory for general systems, as well as some nice interpretations of it that you can read. And we can discuss about it later. So from next class, Professor Vukovic is going to start with normal mode expansions and the quantum part of this class, right? So this is where we are going to end with the classical part of this class. Okay, I think I have gone a bit over time, but thank you all for listening, and see you next on Thursday or in office hours. Okay, so I think I'm going to stop now.
Thank you so much.
Okay,
Yeah.
thank you.
Thanks.
Yeah.